Share screen. Share. I'll go back to this. So I'm gonna go just explain backpropagation through time. Did you reached this part, right? So you heard me talk about this part, no? Yes.
Honestly, I don't know.
Okay.
أنا
Right. So I'll repeat it again, right? So the idea is I want to train a recurrent neural network, and in this architecture we have a many-to-many paradigm. So basically, at every step, I output something. Let's say it's a named entity recognition or some tagging or whatever the application is, yeah, or it's translation, machine translation, or something like this. Okay. So how do I do this? I initialize the weights like any neural network. Initialize the weights to random. Initialize the initial state H0 to random or 0, and then I compute these hidden states by multiplying the input with the with WHX, multiplying the previous hidden state with WHH, that gives me this hidden state. Multiply this hidden state with WHY, that gives me the output at this time step. And then I use the hidden state from the previous step, so multiply this by WHH, multiply the next input by WHX, that gives me hidden state 2, multiplied by WHY, that gives me, the output at time step 2, and so on. So I can compute all these output based on the input sequence. Note that this output depends on all the sequence, yeah, so all the previous steps, because it's really the hidden states are encoding the whole sequence, yeah. So final output at this step depends on the sequence. That's the power of recurrent neural networks. Yeah, so we're doing forward path through the entire sequence to compute loss. And how do I compute loss? I know the actual labels. I know what is this supposed to be. Yeah, this is, for instance, if this is named entity recognition, this would be person, and maybe I predicted it as a location, and so this is an error. So I can compute a loss, whether cross entropy loss or mean squared error, depending on the application. Okay, but I can compute a loss and backpropagate this loss through time. So what does this mean? It means backpropagate it through this network backwards. Yeah? So I go from here, multiply the gradient by WHH and WHX and WHY to get to the to the gradient at this step, and then the gradient multiplied again by the W to get to this time step, and this W again to get to this time step, until you backpropagate it throughout the whole sequence. Yeah, so this is how I update the weight. So I update the weight successively by multiplying by the gradient by the weight matrix, in a nutshell. Okay, so we backpropagate through the entire sequence to compute gradient. Then we looked at an example, which is the character level language models. So I'm not going to repeat this. We'll go back to backpropagation through time. So there is an issue with backpropagation through time, a couple of issues. One of them is huge training time. The sequence length is very long. So basically, in order for you to do one update of the weight, right, you'll have to backpropagate through the whole sequence, and that takes a lot of time to compute. You can do really an update of a weight until you have computed all the output, and then you compute the loss, and then you backpropagate it through the whole sequence. So this takes a lot of time. Second thing is the exploding and vanishing gradients. We've talked about this before. What does this mean? It means that by the time the gradient is backpropagated through the whole sequence, it either explodes or vanishes. So let's look at why this happens. This happens because of the following. There's successive multiplication by the weight matrix W. Yeah, we'll see this in more detail next. But the solution to this is to avoid, this huge training time and exploding and vanishing gradient, is to do truncated backpropagation through time. So all the implementations that you will see, so we have an assignment on this for this week, uses this truncated backpropagation through time. So you do, you go through a certain fixed number of time steps. You don't go through the whole sequence, you go through a fixed time step. You run forward and backward through chunks of the sequence instead of the whole sequence. So basically I go through, you read, let's say 6 time steps or 7 time steps, compute the hidden states, compute the output over these 7 time steps, and compute the loss only on these 7 time steps. Yeah, so you still have more in the sequence to read or to process, but you're gonna compute the partial loss after a certain fixed number of time steps. Okay, and you backpropagate this through this sequence. So now you're not multiplying by W to the power of n, where n the length of the sequence, you're only multiplying by W to the power of 7. So you're not really exploding or vanishing the gradient too much. Yeah. Then, yes. Questions? Okay. So now we do this, and now you pass the hidden state. So you continue computing the hidden states, right? But now you pass the new fixed length sequence, part of the next part of the sequence. Yeah. So 7 or 6 time steps. You know, compute the hidden states, compute the output, and then compute the partial loss on only these 6 time steps. And then you backpropagate only through these 6 time steps. Yeah, so only backpropagate through these 6 time steps to compute the updated weight. And then you backpropagate, and then you continue. So now you have the hidden state from the last time step. You pass it on, multiply the weight by the next input, and so on. Compute the loss, the partial loss, and you backpropagate it through these 6 or 7 time steps, 6 time steps. Okay, and that's how you basically you override this issue of backpropagation through time, this exploding and vanishing weight. Yeah. So the problem with this is that you lose long-term dependencies. So the output here depends only on the input sequence. It depends on the whole input sequence because you're passing the thing, but the backpropagation, you know, doesn't take into consideration the whole sequence. So you lose some long-term dependencies. Yeah, that you cannot really basically capture dependencies from here. The input sequence here does not have an effect on the gradient. Yeah, so really it doesn't affect the gradient here. Okay, you're really looking at the gradient only few time steps before. So looking at only the few input sequence steps, just a few of them, not the whole sequence as you're updating your weights. Okay, so there's a solution to this, which is called long short-term memory networks. This is LSTM for short. This is the one you're gonna use in the assignment. This is really the most popular type of recurrent neural networks that you see these days. There is also BERT models, which is something relatively new, but I mean, the state of the art or the most common one, at least seen in most implementations, is this long short-term memory network. We're not gonna dwell a lot into the details of it, just know the architecture so that you can actually train it in the assignment. So the vanilla RNN, vanilla recurrent neural network, as we said, you stack the previous hidden state with the input, xt, at time point t. You stack them into one matrix, and then multiply this by the weight matrix W, which is a concatenation of WHH and WHX, and then pass it through nonlinearity, typically 10H, to get the next hidden state. Yeah, so this is the vanilla RNN. And this, as we said, suffers from vanishing and exploding gradients because of the successive multiplications with the weight matrix W. Because you do this, 10 times steps, or 20 times steps, or 30 times steps, and that involves multiplying by W successive, the gradient by W successive. So let's look at this. Yeah. What happens is really the gradient passes. So forward pass is the black arrows, yeah, to get from H0 to H1, and then from H1 to H2, and so on. And the red arrows are the back propagation, yeah, back propagation of the gradient. So start with the red, you're passing it through nonlinearity, multiplying by W, and then you're passing it through nonlinearity, multiplying by W, and so on. Yeah, and this successive multiplication by W, so as if you're doing W times W, that's W squared, times W, that's W cubed, times W, that's W4, and so on. Yeah, so if I have only 4 time steps. This successive multiplication of W basically, and repeated 10H, causes the gradient to explode or vanish. Particularly, it explodes if the largest singular value of the W matrix is greater than 1. That causes exploding gradient because you're multiplying by a factor that is greater than 1. You can assume if this was just a scalar and W was a scalar, then if you multiply with W and it's greater than 1, then it will explode. Yeah, and if W was less than 0, or the largest singular value is less than 1, or the largest singular value is less than 1, this causes the vanishing gradient. Because you're multiplying, you know, let's assume it's a scalar, you're multiplying by a value that is less than 1, that causes the value to diminish. Every time you power, every time you multiply by w, the value diminishes or vanishes. Yeah. So just a side note that depending on the largest singular value of w, either you have a exploding gradient or a vanishing gradient. Okay. Long short-term memory network, or LSTM. This is how it looks like. It's a little bit complicated, so try to follow. So as previously, you have a hidden state, previous hidden state ht minus 1. You stack it with the current input xt. You then multiply this by w, yeah, a matrix w, which is a concatenation of two matrices, whh and whx. Pass it through some nonlinearity, and then you get 4 gates. So you have 4 gates in the LSTM, in the recurrent and the LSTM neural network. You have a forget gate, an input gate, a gate, and an output gate. Yeah. So for a lack of better name, I call it gate. Yeah. But they are just called F, I, G, and O. Okay. What does these guys do? It takes the output of multiplying W by the stacking of HT minus 1 and XT and does something with them. Yeah. For the forget gate, it outputs this with the previous CT minus 1. So it's similar to, so as if you have two hidden states, HT minus 1 and CT minus 1. Yeah. This gets pointwise multiplied. So F with CT minus 1. And then you have I and G, you do pointwise multiplication. And then you have the output just passed directly. Yeah. So you take F pointwise with CT minus 1, and C0 would be again initialized at random. And that gives you, you add it to the pointwise multiplication of I and G, and that gives you the current CT. So the cell value. So this is the LSTM cell, and that's the cell value, CT. And then you pass this to a nonlinearity, 10H, do pointwise multiplication with the output gate, and that gives you the next hidden state. Yeah, so you have CT and HT, and that goes to another cell, LSTM cell, which looks exactly like this. You do the same thing, you multiply, you stack HT with XT plus 1, you multiply by W, stack and multiply by W, then you have these 4 gates, I, F, O, and G, and then you compute basically from it CT and HT using this architecture. Yeah. So what is I, what is F, what is O, and what is G? I and F and O typically are sigmoid. So you pass them through some sigmoid. Yeah. So this nonlinearity here is a sigmoid for I, F, and G. For I, F, and O. And for G, it's a tan H. Yeah. And then this is applied on the W of the stacking of HT minus 1 and XT. Then you compute CT, as we said, pointwise multiplication of F and CT minus 1, and then adding this to I, pointwise multiplication with. And then you do the HT is basically O pointwise multiplication of 10H of C. Yeah, so I mean, the details of why this is like this is not really clear. I mean, you can read the original paper, the references here, but it's not really very clear. The intuition is that you do some sort of a forgetting. You want to forget some input sequence. So basically, you have the option of forgetting some input sequence. So you can, and that's what the role of F is, to kind of say, okay, how much should you keep from the previous cell? Yeah, so you have this CT minus 1 is the information you kept from in the previous cell, and you say, I want to forget this thing. Basically, I don't want the dependency from the past sequence to play a role in this current output. So you have the flexibility of deciding for every output whether you should take into consideration long-term dependencies or not. Yeah, just an intuition.
Sir?
Yes.
طب نحن we have a forget gate, right?
Yeah.
Which basically tells us إنه أي part من الانبوت ما بدنا إياه بقى.
Exactly.
بس ما then we are adding the input بعدين إنه we are using dot this thing ما بعرف شو اسمه مع ال I Yes, and then we're adding it مع ال F وال CT minus 1. So basically, we are still using the whole input. But the whole point of forget is to forget some of the input.
Yes, so you basically have the freedom of setting these values, right? So that the network has the freedom of setting the weights and setting, you know, some of these values, so that, right, you can forget some of the previous cells. That's really how it is. Yeah, I see that you're saying, okay, but you have ing as well, yeah, and these are from the previous computers from the previous thing, but you're adding them. You're not really basically. The forget gated rule is to say, okay, forget some of the previous things, right? So if it's set to 1, you kind of keep. If it's set close to 0, you kind of forget the CT minus 1, but you still have something from the current input. Yeah, you have something from the current input and the previous hidden state. Yeah. So this is really just an intuition, Rodrigo. It's more complicated than this. Yeah, really quite complicated, and it's not very intuitive. So really, it's not super intuitive. I'll try to give you in the next slide why is it helping with the vanishing and exploding gradient, but this is pretty much what you're required to know from this. If you're more interested, you can read the paper, read some, you know, posts on this, but I doubt there will be a better explanation of this. Yeah.
Okay, thank you, sir.
Okay. So there is also a simpler architecture known as gated recurrent unit that also exists. So I don't need you to know all the details about it. Just know that there is GRUs. So this is also something that is a recurrent neural network that has, you know, the capability of dealing with the vanishing and exploding gradient. So why do they have this capability of, you know, dealing with vanishing and exploding gradient? It's because of these Cs, right? These Cs kind of allows an interrupted gradient flow. So basically, as your gradient is passing through some nonlinearities and getting multiplying by W, the Cs allows you to pass the gradient without multiplication with any W's. Yeah, so you can go through this connection, through this red path, and pass the gradient from this cell to this cell through this, you know, red path without going through any multiplication with that, and that allows the network to kind of pass gradients if it needs to. Yeah. So this is similar to ResNet and convolutional neural networks, where you had these residual connections to pass the, you know, bypass some of the you know, deep layers and pass gradients and you know, input values through the network without having to go through multiplications with weights. Yeah, same concept appears through this the cells of the LSTM. This is really all I want you to know. As you do the assignment, you will see that this details doesn't matter much in how you train the neural network. Again, it's nothing but backpropagation and setting some weights. Okay. Finally, we'll end with this, and then we'll start something else, a new topic today, which is basically meta-classification. Okay, so bidirectional LSTMs, this is a very powerful model, and it's nothing but you can assume that it's a 2-layer LSTM. So you have, you can do this in any recurrent neural network, but I'll illustrate it using LSTMs. So it takes into consideration the past, the present, and the future. So you have one that is in forward direction, so forward layer, which is nothing but LSTM cells, as we've seen them in the previous 2 slides. And then this, you know, takes care of the input in the forward direction. So I'm getting dependencies in the forward direction. So whatever is in, you know, the previous time step affects the output in the current time step. Yeah. And then you have a backward layer, which takes into consideration dependencies in the opposite direction. So the LSTM is basically, you're taking the input from time step capital T, and that decides the input sequence, or decides the output at step T minus 1. Yeah. So basically, it's going in the opposite direction. Yeah. So really looking at the future input to decide on the, you know, previous output. Then you combine these 2 things to get to the, you know, the output at time step T. So time step T looks at the, you know, input xt, looks at the, you know, hidden state from the previous time step ht minus 1 and the hidden state from ht plus 1 using the backward layer. Yeah, and that gives you really the capability of looking at both the previous input and the future input. When does this help? It helps in scenarios like translation, like, you know, so in translation, for instance, sometimes you need to find, you know, the word at the end, particularly in German or languages like this, to be able to determine, you know, the tense of the verb, or determine, you know, what is the how the verb should look like, or what is the translation should look like, and so on. Yeah. So in German, for instance, you can put, I think, the subject at the end, and so you might want to wait till you read the subject to be able to decide on the tense of the verb in English, for instance. Yeah, that it's a he or a she rather than we or I. Yeah, things like this. What is it in terms of training or in terms of you know, building a model? Is nothing but, right, just 2 layers of LSTMs stacked on top of each other. Okay. You have also deep recurrent neural networks, typically, you know, 2 or 3 layers, and these are just, you have the input, and then you have multiple layers of recurrent cells or recurrent layers. So basically, every layer has its own weight matrix, and then it feeds to the next layer. So instead of directly predicting the output based on this hidden state, I pass this to another layer, which has its own weight matrix, WHH and WHX. In that case, WHX would be multiplying this hidden state by, you know, by the weight. So you have some weights here to multiply these hidden states with them. The same weight, of course, across all of them. And that gives you another hidden state. And then this hidden state gets multiplied by another weight to get to this hidden state. And finally, this hidden state is multiplied by WHY to get to the output. Yeah. And this could be, of course, an LSTM, or could be just a vanilla RNN. So if it's vanilla RNN, then as we said, it's a 10H W HT minus 1 and HT. Yeah. So basically, this is how the general, every layer has its own weight matrix. Yeah. If it's an LSTM, then you'd have again WL is a weight matrix for each layer. You have for each layer a weight matrix, and you backpropagate through the whole network. Yeah. So you backpropagate through the whole network to update these 3 weight matrices in this example. Yeah. Again, nothing more than just saying, all right, I want to create a multi-layer recurrent neural network in the code, and just basically you would have 3 weight matrices that you have to update. Okay. And the assignment you will do, I think, just the plain right LSTM, so single layer LSTM. That's I mean, the rest are really easy generalization of this. So if you're done on a regular, you know, 1 layer LSTM, you will be, or recurrent neural network, you'll be able to train multi-layer without any issues. Shouldn't be a problem. Okay. I'll stop here. I'll stop the meeting and restart again, and restart the new topic. Have questions? Okay. So I'll ask Shadi to do again a lab session this week for you to kind of get acquainted with LSTMs and recurrent neural network, and then you should not have any problems with the assignment. It will be very straightforward. Okay. Good.
Professor, can we discuss the project?
Yeah, we can discuss the project. What do you want to discuss about the project?
انه نحن انه اذا we're going على schedule نحن هلا وين المفروض نكون صرنا بالبروجكت؟
So you should put the methodology and related work by 19th of April. So I think in how many days? In 5 days. 5. Yeah, so 5 days you should have the methodology and related work. So basically, you should say now I'm going to train a neural network. Let's say if you're doing neural networks, I'm going to train a neural network on you know, on my project. This is how the architecture is going to look like. It's a recurrent neural network or a computational neural network, and you know, this is really what state of the art or related work, meaning what has other people done, and if there are any work on this, you know, from previous papers, something like this, just list them. Yeah? So basically, these are, you know, a small paragraph about each one. That's where you should be at now.
اوكي وكمل assignments the grades. Shadi corrected assignment 1 then assignment 3 uh, which is a total of 2 out of 8 that we submitted.
Okay, I'll follow up with him. He should have you know, have updated the, he's correcting, but I'll ask him to speed this up a little bit. Yeah. Anyway, the drop and add, not the drop and add, the withdrawal deadline has been to extended till the end of the semester, correct?
Yes.
Yeah, and you also have these pass and fail options. So, I mean, this should not, the grades should not affect you much, but I'll ask him to speed it up. Yeah.
Okay, وبعدنا a total of 12 assignments.
Yeah, so I think so. We have one assignment coming up, right? After this recurrent neural network, and then another assignment. So yes, 2 assignments month. Okay.
All right.
Okay, guys. The next 2 assignments should be relatively easy. Yeah, so really easy ones. One is going to be on this meta classification or this ensemble learning, and then another one on unsupervised learning. Yeah, which is the last 2 topics we're going to talk about. Okay. Like, we resume again in a bit. Okay. Stop recording.